So notice, instead of calling this value P, we now refer to it as A sub 0. And notice that's our initial amount or initial population. K is used instead of R, and that is either our growth rate or our decay rate. When K is positive, we have exponential growth. When K is negative, we have exponential decay. So what we have is decreasing or decaying. So here's an example of a problem where in the year 2000, the population of the Palestinians in the West Bank, Gaza Strip, and East Jerusalem was approximately 3.2 million. By 2050, it's projected to grow to 12 million. So we're using this same model. Notice how much this looks like continuous compounding in the financial formula. And it really is the same type of growth. So we basically want to find the exponential growth function that models the data. For part A, part B, we want to find out when this population will be 9 million. So notice we're using this model. The T is the number of years after 2000, the year 2000. So notice when T is 0, A sub 0 is the 3.2 million that we were told was the population in the year 2000. So the model looks like this. A equals 3.2 times e to the kt. Now to find K, we use the fact that in the year 2050, the population will be 12 million. So we replace T with 50. That's 50 years after the year 2000. And the A is now going to be replaced with 12, but A naught is still the 3.2. All right, we know this is growth, so we know we're going to get a K that's bigger than 0. So we plug in 12 for A, 50 for T, and this allows us to find K. So e to the K times 50 is 12 divided by 3.2 when we divide both sides by 3.2 to isolate the exponential. Now we can apply the natural log to both sides. And remember, the natural log has base e and is applied to an exponential whose base is e. So we simply get K times 50 on the left side, and we get the natural log of 12 divided by 3.2 on the right side. So to solve for K, we divide by 50. And notice that the natural log of 12 divided by 3.2 divided by 50 is approximately 0.026. This is our K value. So our model is A equals 3.2 e to the 0.026t. And that is the model for this situation. So to find when the population is going to be 9 million, we replace A with 9 and solve. And notice we're going to divide both sides by 3.2 to isolate the exponential. And now we're going to apply natural log to both sides of the equation. And now we use the fact that the natural log of e to the 0.026t is simply 0.026t. And now to solve for t, we divide both sides by 0.026, and we get that t is approximately 40. So 40 years after 2000 puts us at 2000 plus 40, or the year 2040. So let's look at an application problem. The population of Adamsville grew from 9,000 to 15,000 in 6 years. Assuming uninhibited exponential growth, what is the expected population in an additional 4 years? Round to the nearest whole number. All right, so one of the things we need to realize here is that when you are assuming uninhibited growth, so that's very key. Uninhibited exponential growth. You are using this model where your amount or population will equal the initial population times e to the kt. So this model shows uninhibited exponential growth. So we were told that the population grew from 9,000 to 15,000 in 6 years. So what we're saying is that a sub 0 is 9,000, a is 15,000, t is 6. This will allow us to find k. So we replace a with 15,000, a naught or a sub 0 with 9,000, e to the k times 6. So we want to isolate our exponential. So we're going to divide both sides of the equation by 9,000. So these, on the right side, 9,000s divide out to give 1. On the left side, we get 5/3. And that equals e to the 6k. So we are going to apply the natural log to 5/3. And we're going to apply the natural log to e to the 6k. The base of a natural logarithm is e. So the natural log of e to the 6k is the exponent you apply to the base, which is e, to get e to the 6k. So that result is simply 6k. On the left, we have the natural log of 5/3. To solve for k, we divide both sides of this equation by 6. And our k will be approximately this result. We're going to use our calculator to find this. Notice you have to parenthesize 5/3. So k is approximately 0.08514. And we are going to use this in the model so that we can refine the model. The model is a equals a naught, which was our 9,000, e to the 0.08514 t. So that's our basic model. Now when we are asked what is the expected population in an additional 4 years, then we know from 0 to 6, we went from 9 to 15,000. An additional 4 years would be what happens 10 years from the beginning of our measurements. So we're going to let t equal to 10 since we we know what happens in 6 years. We want to know what happens in 4 years after that. So we let t equal to 10. And so our amount of the population will be 9,000. Sometimes, anyway, let me not make that comment. E to the 0.08514 times 10. So that's 9,000 e to the 0.8514. So when I multiply by 10, the decimal moves 1 unit to the right. And I use my calculator to do this calculation. And I was told to round to the nearest whole. And I get 21,086 when I use my calculator. So in an additional 4 years, the population is about 21,086. And notice we expect that to be greater than 15,000. Since it is an exponential growth function, we knew that we should have more than we had in 6 years. All right, let's look at number 4. During a research experiment, it was found that the number of bacteria in a culture grew at a rate proportional to its size. That's another way of saying that the model we're using is A equals A naught e to the kt. At 8 a.m., there were 2,000 bacteria present in the culture. So that's when we're going to start counting. That's our initial value. A naught or A sub 0 is 2,000. At noon, the number of bacteria grew to 2,400. So A is 2,400. T is 4, and this time is being measured in hours. Okay, before in the previous problem it was being measured in years. Now a time unit, it's clear, is an hour. All right, so we make the replacements. We let A equal 2,400. We let A naught equal 2,000. We replace T with 4. And we want to isolate our exponential. We divide both sides by 2,000. And on the left, we get 6/5. On the right, we get e to the 4k. We take the natural log of both sides. And hopefully the thing we understand is that when we apply the natural log to e to a power, we simply get the power, which in this case is 4k. So to solve 4k, we need to divide both sides of this equation by 4. And so we use our calculator. You must parenthesize that 6/5. We use our calculator to get the result. And we get that our K is approximately 0.04558. And that's approximately our value of K. So we can refine the model. The model is A equals 2,000 e to the 0.04558t. So when we are asked our question, which is how many bacteria will there be at midnight, we have to count how many hours are there from 8 a.m. to midnight. 8 a.m. to 8 p.m. is 12 hours. 8 p.m. to midnight is 4 more hours, so that's 16 hours. So we want to let t equal to 16. And our amount of bacteria in the culture will be 2000 e to the 0.04558 times 16. So that is 2000 times e to the 0.72928. And we are going to let our calculator give this to us. 2000 times e to the 0.72928. And I get to the nearest whole number, I get 4,147. So at midnight, there are about 4,147 bacteria in the culture. All right, and so we know that this should have been more than 2,400. And so certainly that is what we have gotten.